Now you look at these three images that are shown to you, these three situations actually. Assume the first one is a Ferris wheel or a giant wheel rotating like this. Second one, clearly it's a fan rotating. Third one is a diver, fine, jumping from a springboard as it is mentioned. What is common to these three systems? What is one thing which is commonly happening in all three cases?
Circular paths.
Can you repeat?
Circular path.
Circular path. In the third case, where is the circular path? Like where exactly is
Like
the
curved, sir.
ah,
Curved. Curved.
curved path? Okay, okay, fine. But curved paths we discussed before also, no? Like bob suspended from a string, it follows a curved path. That's okay. It's not that uh, what we discussed earlier should not be seen here. Okay, curved path is one thing. Any other answers? What is common to these three systems? Or just that curved path, that word is a little vague. Can you be more precise in your answer?
The rotational motion.
Rotation. Yes. Okay. In all three cases, there is rotation happening. Okay. Let us discuss this also in detail. How do you decide if a system is rotating or not? Like on what basis can you identify rotation? I mean, by looking at it, yes, in our daily life, we are used to telling whether we are used to it. We can easily tell whether an object is rotating or not. But what exactly do you think is helping us identify that the system is rotating? Any idea, anyone? Okay, fine. See, we subconsciously register the relative position of particles. Okay. For example, in the first case, let's consider this yellow cabin and okay, the opposite yellow cabin. Let us consider these two. As the Ferris wheel or the giant wheel rotates, our brain automatically registers the fact that the line connecting these two is rotating. Its orientation is changing. Okay. Or their relative position orientation is changing. You can say like that also. Consider this as uh, object A or particle A and consider this as particle B. How do you draw relative position? Basically, it's the position of one object, one particle absorbed by another particle. So position of A relative to B is like this at this instant. At at a later instant or at the next instant, this position vector's orientation would change. Our brain subconsciously registers all that the relative position is changing. That is how we can identify that an object is rotating. Same thing with the fan case also. You consider one particle here, call this as A, and some other particle here, call it B. Now position of A relative to B at this instant is like this. But at a later instant, this vector's orientation would change. Okay, definitely maybe B comes to this position and A goes to this position. Then the relative position vector becomes like this. Okay, we'll subconsciously be observing all that. And that is what makes us identify that the system is rotating. In case of the person also, okay, if it's a single point, no, you cannot tell if a single point is rotating or not. In fact, for a single point, rotation is undefined. If there are 2 points in a system, okay, then only you can tell whether the system is rotating or not. So indirectly, you will be connecting those 2 points with a straight line. Not indirectly, what I'm saying is subconsciously you'll be connecting those two with a straight line. And if that straight line's orientation is changing, then you say the system is rotating. Okay. So in all these systems that you see here, rotation is a common thing. Okay. Now what's the big deal with rotating systems? let us recollect a small point from circular motion. Suppose an object is moving along a circle like this. Let's say it's moving in a circle of radius r with an angular velocity omega. Now, corresponding to that angular velocity is the rate of rotation. Okay, corresponding to the rate of rotation, there will be a speed, particular speed at which this object is moving. Can one of you tell me how v, r, and omega are related in circular motion? How is linear speed related to angular speed omega?
So V is R omega.
Good. V is equal to r omega, where omega is the rate at which the object is rotating, object or system, and r is the distance of the object from the center of the circle or the circular path that it is following. Okay. Now, see, the third case, the diver is not a rigid object. Okay. Human body is flexible. Fine. But the first two cases, the Ferris wheel and the fan that you see, ceiling fan, these are rigid objects. Fine. We'll talk about uh, rigid objects also in detail. There is a mathematical idea that can be applied there. But as you see, in all these cases, there is rotation, means there is a certain rate at which the system is rotating. Okay. So the Ferris wheel has a particular omega. The fan which is rotating, it will have a particular angular velocity omega. The diver, okay, when they, what do you say, when they jump off, they create that rotation also. Okay. So the diver is also rotating clockwise here, as you can observe. Arrows are also given. Fine. So the system will have a particular rate of rotation. In fact, it's possible that different points of a system have different rates of rotation also, which is possible in the third case. Okay. But in the first two cases, in case of rigid bodies, the rate of rotation has to be fixed. Okay. We'll discuss all that in detail. Now you observe the fan. Consider two particles of it. One of them here at a distance r1 from the center. That green particle will follow a circular path of radius r1 like this as the fan rotates. And you consider another of its particles. Let's say this blue one. Blue one, assume it is at a distance. Okay, wait, I'll put it on another wing. Consider another particle here, the blue one. Let's say it is at a distance r2 from the center. Then as the fan rotates, the blue one also will follow a circular path like this as the fan rotates, right? Now, tell me this. Let's number these blades as, okay, let this be 1, let this fan blade be 2, this one be 3. Will all the blades of the fan complete one rotation in the same time always or not? Generally, in case of a ceiling fan, will every blade of the fan complete one rotation in the same time or not when the fan is switched on? Rishi, what do you think?
Sir, can you repeat your question?
When the fan is switched on or when you rotate the fan, will the time taken to complete one rotation be same for all three blades of the fan or will it be different?
Yes, sir, because the fan speed is same.
It will be the same. By the time the first blade completes one rotation, the second one also will complete, third one will also complete. Saket, do you agree with that or not?
Yes, sir.
Okay. And what about the giant wheel case? Vanilla, you tell me. Let's number these chairs or seats that are there. Let's call this as 1, this as 2. Suppose the first seat completes one rotation. By that time, will the second seat also have completed one rotation or not?
Yes, sir.
Yes. Okay. Usually in rigid systems, in rigid objects, that is how it is. Okay, they don't rotate at different rates, they all rotate at the same rate. Okay, now consider that fan case itself. Call the green particle as A and the blue one as B. They both have the same rate of rotation, means they both rotate by the same angle in the same amount of time. Okay, you can rotate any solid objects that you have in your hand or around you and check. By the time one particle rotates by some angle, every other particle also would have rotated by the same angle. Okay, so omega is common for A and B, the particles A and B. Now they are moving in circles, we know, and we also know that in circular motion, V is equal to R omega. That's how the linear speed and angular speed are related. So we can say that speed of A, okay, speed of the particle A is equal to R1 multiplied with omega, and speed of the particle B is equal to R2 multiplied with omega. And R1 is smaller than R2. So speed of A will be less than speed of B. Okay, you all must have known this from everyday experience also. Particles which are closer to the center rotate slowly or move slowly. I should not say rotate slowly. They all rotate at the same rate. Their speed will be less. They move slowly because to complete one rotation, A has to move in a smaller circle. But to complete one rotation, B has to move in a larger circle. So B will have to maintain more speed than A. Okay. So greater the distance of the particle from center, greater the speed with which it will have to move. Now tell me, how many particles are there in that fan? How many points, separate points can you identify in that fan? How many individual particles exist in that fan? Or how many points can you mark on it?
Can't mark them.
What did you say?
There's too many points.
Ha. We can mark infinite points. Fine, on that fan. Now, if there are infinite different points, then there can be infinite different velocities. Fine, at each distance from the, what do you call, center of the fan, you can consider a point. Let's say the total distance to the edge of the blade is 1 meter. Will they be one? Yeah, it could be 1 meter long. Let's say the distance from here to here is 1 meter. In that 1 meter itself, you can identify infinite number of points. And each point is at a different distance from the center of the fan. So infinite different velocities will be there. Same with the Ferris wheel, same with the diver also. Okay. So if there is rotation happening in an object or a system, there will be infinite different velocities of particles in that system. Fine. Now, one of you tell me, what is the formula for linear momentum? Basic formula for linear momentum. Aishwarya, you seem to have unmuted, but I didn't hear anything. Unmute, wait for a second and then answer. Anyone, what is the basic formula for linear momentum?
Mass into velocity.
P is equal to mv. Okay. Now, if there is a system like this, which is rotating, if you know, not if you know, if there is rotation, you know that there will be infinite different velocities in that system. And if you are asked to calculate its linear momentum, P is equal to mv, how will you calculate this? Every particle of the system could have a different velocity. Then how will you find out? This is for single particle. P is equal to mv is for a single particle. Okay. If you are asked to calculate, or if you need to calculate the linear momentum of a system, then you will have to do mass of one particle of the system multiplied with its velocity plus mass of second particle of the system multiplied with its velocity and so on. up to the nth particle of the system multiplied with its velocity. You have to include linear momentum of all the particles of the system. Now, if there are infinite different velocities, you can't even take velocity common. Okay, there will be infinite different terms, and practically it is impossible to add infinite number of terms one by one. You need some mathematical ideas. Okay. Next, what is the formula for kinetic energy of a particle? Rishi, tell me the formula for kinetic energy quickly.
Half mv square.
Half mv square. If a mass m moves with speed v, then its kinetic energy is half mv square. Okay. But if there is rotation happening in a system, the different particles of the system have different velocities. You can't say all the mass is moving with this velocity. Okay, different particles have different velocities. Then for kinetic energy of a rotating object, you have to consider the rotating object as a system of particles. That's why the name of the chapter is System of Particles and Rotational Motion. Whenever you see rotation happening, even if it's an object like a fan or a water bottle or a pen spinning like this, you will have to think of it as a collection of infinite particles. Okay, it becomes a system. You don't call it a single object anymore. You call it as a system of particles. Okay, so kinetic energy of the system will be kinetic energy of the first particle plus kinetic energy of the second particle, and so on, kinetic energy of the last or the nth particle of the system. Again, you can't literally practically sit taking each of their velocities and adding them up, because there will be infinite terms, impossible to calculate one by one. So you'll have to use some ideas to get this. In this chapter, these are what we are going to discuss, not just momentum and kinetic energy, some other things also. Basically, what we are going to learn is how to deal with systems which have rotation happening. Okay. And in your syllabus, as far as your syllabus is concerned, we will only be studying about rigid objects or rigid bodies. Okay. Can any of you tell me the meaning of the word rigid? Or when do you call an object as a rigid object?
Or when its molecules are very tightly packed.
Tightly packed. Okay. Oh, fine. Yeah, to some extent, your answer is correct only. Rishi, you tell me, can you name some rigid objects that you see around you?
Or brick walls.
What did you say?
Walls as well.
Wall. Okay, the brick wall. Any other? Okay, someone else. Saket, tell me any rigid object that you can think of.
Sir, a whiteboard.
Whiteboard. Okay, fine. Marker board, let's say. Basically, rigid means non-flexible. You can't bend it. You can't deform it. That is what is rigid. Or as long as we don't disturb it, it doesn't get deformed. Okay, let's talk about that kind of rigidity. There's no object which cannot be bent or broken. Okay, it all depends on the force that you apply. But as long as we don't disturb it, let's say it doesn't bend or get deformed, let's call those objects as rigid objects, rigid bodies. Aishwarya, tell me an example of a rigid body that you can identify around yourself. Think about it. Vanilla, you tell.
Bottle, sir.
Bottle made of?
Metal.
Okay, steel bottle, let's say. Fine. So there are a lot of objects which we can say are rigid. But see, any of these can be deformed by applying the sufficient amount of force. So no object in the universe is perfectly rigid. Okay. But as long as you don't disturb them, as long as you don't apply a force on them or don't apply a very strong force on them, they can maintain their shape. So rigid bodies are basically objects that do not get deformed significantly. And it all depends on the situation. Okay, see, like the water bottle itself, if you simply hold it and drink water from it, it won't get deformed. Or even if it gets deformed, it's not noticeable at all. But the same bottle, if you fill it with water, same steel bottle, fill it with water and top it to the ground, it's quite possible that it develops some dents when it hits the ground because the ground exerts a very strong force on it, an impulsive force, which deforms the object. Fine. So for now, we are only considering with what we identify as solid objects in daily life. Solid objects are rigid bodies. Solids maintain their shape, we say, no? But it's not that solids cannot be deformed, they can be. But when you use them in a gentle manner, they don't get deformed. So those are the rigid bodies that we are going to consider. Okay. Like in the last chapter, I told you, work energy power, when we discussed collisions, we discussed that every object undergoes deformation to some extent. Okay, when two objects collide. But during collision, what happens? Impulsive forces will act. So their deformation is possible. For now, we will consider ideal or perfectly rigid bodies. Fine. So that flexibility in those objects we will not consider as of now. Okay. Now we can write mathematical expressions also based on the simple fact that a particular object is rigid. Consider some random object like this. It could be a stone or whatever it is. We are looking at the cross section. Fine. And imagine some particles inside it. See, there will be infinite number of particles. I can only show a few of them. Fine. Assume this is a rigid object. Consider two particles. Let's say this one, call it as A, and say this one, call it B. If the object is perfectly rigid, can one of you tell me anything about the distance between these two particles? Anything you can say about the distance between them if the object is perfectly rigid? I'm not asking how much the distance is, that you cannot tell, who knows. But any characteristics of that distance?
Sir, the distance is very small.
How much is very small according to you, Vanilla? What distance do you call as a small distance?
Like we cannot measure the distance between them, sir.
Why can't you measure? You can literally put a scale on the screen and measure. It is measurable. Not every pair of particles is that close. No, one particle and the next particle are very close. That distance cannot be measured, maybe. But two far away particles of the same object can be measured. Like water bottle itself, you take, you can measure the distance between the cap and the base of the bottle. No.
Okay, sir.
Huh. Any other characteristics any of you can mention? Okay. As this rigid object moves, as this rigid body moves, what happens to the distance between two of its particles? Will it remain same? Will it change?
It remains same.
It remains same. See, if two particles can come closer, then that is deformation. No? In a rigid body, that is not allowed to happen. If two particles can go farther also, that is deformation. In rigid body, that is not allowed to happen. So the condition in a rigid body is that the distance between any pair of particles must be constant. Constant or fixed, you can say. It should not, that distance should not undergo any change. See, in a real life situation, when you apply enough force, particles can be brought closer, particles can be taken far also. But when you don't apply that much force, there won't be much change in the distance. In an ideal case, there will be zero change in the distance. Distance will be fixed. Okay, so this is one thing you have to remember about a rigid body. Distance between any pair of particles must remain constant. Okay. Now, imagine two particles like this. Again, let's name them as A and B itself. So they may have some distance between them. Now, distance between A and B should be fixed. Distance between two particles of a rigid body should be fixed. Does that mean rigid body cannot move? It can move. You know, rigid objects can move, solid objects can move. So A can move, B can move, but the distance between them should not change. Can any of you tell me a relation between their velocities? See, we know that A can move, B can move. Any particle of the rigid body can move. Okay, if it is free. But even when they move, the distance between them should not change. So let's say A has a velocity VA. I'm not mentioning the direction and all. It has some velocity. I don't know. B has a velocity VB. Can any of you tell me a relation between VA and VB such that the distance between A and B does not change? There must be some relation, no? They can't be completely independent of each other because the distance has to remain fixed. Think about it.
PA equal to VB, sir.
Okay, good. That is one possibility. Fine. So we are discussing about relation between velocities. Of any pair of particles. One pair we have considered is A and B. One possibility is that VA is equal to VB. Correct. See, if both have same velocities, they'll undergo equal displacements in equal intervals of time. Let's say in a short interval, A gets displaced from here to here. Okay, it all depends on how A is moving. I'm assuming A's velocity is in that direction. So let's say A gets displaced from here to here. Then a few moments later or a few instants later, A will reach this position. Now, if B has the same velocity as A, then B will also undergo the same displacement in the same amount of time. And B will reach this position. And the distance between A and B will still be the same. Okay, if this was some x, this will also be x. So if their velocities are equal, yes, definitely the distance between the particles won't change. But we are considering systems which rotate. Fine. In this chapter, we are going to look at systems and try to describe the physics behind the motion of systems which are rotating. Now, if a system is rotating, like the fan or the Ferris wheel, you know, see, fan is a rigid body only. For practical purposes, you can consider it as a rigid body. You can bend the blades of the fan. I'm not saying that you can't. But when you normally use the fan, the blades won't bend. It's a rigid body. But we know different points of the fan move with different velocities. Okay, like those points A and B, they definitely have different velocities. But still the distance between A and B doesn't change. Okay, so yeah, velocities being equal definitely ensures that the distance between two particles remains the same always. Can you think of some other ideas how they can move without the distance between them changing? Okay. In collisions, we learnt about something called line of impact and speed of approach. Okay, let me ask you one question based on that. Hmm. Assume this is the ground or some surface is there. Let's say there's a particle or a ball moving towards this surface with a speed some 10 meters per second at an angle, let's say 53 degrees. Okay. What is the speed of approach between the ball and the surface? Surface is actually at rest. What is the speed of approach between them? I got one answer as 6 meters per second. Okay, fine. See, approach means what? One object should be going towards the other object. So here, for the ball to approach the surface, it should be moving towards the surface. Now, some of you may say, sir, it is moving with a speed 10 meters per second towards the surface. No, all the 10 meters per second is not involved in bringing the object closer to the surface. For example, you consider something like this. Let's say the ball has velocity 10 meters per second like this. Its actual velocity is 10 meters per second, but is the ball approaching the surface? No. If it moves that way, it will always be at the same distance from the surface. Okay, a few instants later, it will be here. Is it coming closer to the surface? No, it's not approaching it at all. Okay, so all velocity does not become velocity of approach, or all the speed never becomes the speed of approach. Fine. So the question that was given to you, in the question that was given to you, the ball was moving with a speed 10 meters per second at an angle 53 degrees like this. You resolve the 10 meter per second into two components now. One component parallel to the surface, that will be 10 cos 37, 8 meters per second. Due to that 8 meters per second, the ball is never going to come towards the surface. So this 8 meters per second doesn't contribute to approach or separation. Take the other component, 10 cos 53, 6 meters per second. This 6 meter per second is what is bringing the object closer to the surface. So this becomes the speed of approach. Okay, and this is what changes. Okay, that 6 meter per second is what changes the distance between the ball and the surface. Otherwise, the ball will move parallel to the surface. Distance won't change. Fine. Now come back to that rigid body case. A has its own velocity. Two particles of the rigid body we have considered, A and B. A has its own velocity, B has its own velocity. The only condition is that the distance between A and B must not change. Now, what changes the distance between two objects? The velocity of one object towards the other object, which is exactly directed towards the other object, is what you need to consider. So what I'm saying is, suppose A has a velocity like this, as we considered. Okay, let this be VA. Fine. You can resolve that velocity into two components. One component along the line joining them, and one component perpendicular to the line joining them. Blue and green. Let's call them as blue component and red component. One of you tell me which of these components makes A or makes the distance between A and B change. Is it the blue component or the red one?
Red one, sir.
How can the red one make the distance between them change? And why is the blue one not making the distance between them change? Rishi, you only tell me, suppose you are shown only that blue velocity component. With that blue velocity, will A not go closer to B? Will it go or not?
Yes, sir.
It will. Okay. See, it is actually only the blue component which can change the distance between A and B. The red one cannot. Now, some of you may be thinking this way. Sir, why not the red one? Because if A follows that path and goes like this, then the distance between A and B will change. Initially it is X, later it is greater than X. Distance will change, you may say. Okay. We are looking at the component of velocity in the component of velocity along the line joining two particles and perpendicular to the line joining two particles. Indirectly, what I'm saying is something like this. Consider circular motion again. Let this be the center of the circle. Call this as, okay, X. And let's say some object is moving around X in a circle, call it as Y. Now, Y can move around X without the distance between them changing. Okay, distance between X and Y, call it the radius of the circle. Y can move around X by maintaining the same distance R. And to do that, how should Y move? At this moment, its velocity should be directed this way, perpendicular to the line joining them. If velocity of Y is in this direction, the distance between X and Y won't change. I'm not saying it should continue with that velocity. At the moment, its velocity should be pointed that way. At a later instant, when Y reaches somewhere here, its velocity should be in this direction. So indirectly, I mean, not indirectly. So what I'm saying is the component of velocity perpendicular to the line joining two particles does not disturb the distance between them. Okay. Even in this case, the red component does not disturb the distance between them. If you look at it an instant later, okay, actually I'm showing significantly far. Suppose, okay, just a moment. A was the original position. Let's say it reaches A dash now. And you consider that red component, the red component is like this. That red component will no longer, if it maintains the same direction, no, it is no longer perpendicular to the line joining them. This angle is not 90 degrees. When it was here, it was 90 degrees. Okay. So the next instant, that red component, if you take in the same direction, it's not the perpendicular component at all. Okay. So at this moment, we have taken one component of A's velocity parallel to the line joining them and one component of A's velocity perpendicular to the line joining them. It's the component parallel to the line joining them that can change the distance between them. Okay. Suppose B has some velocity now. Let's take in some direction, some random direction like this. Let this be VB, velocity of B. Now that also can be resolved into two components, one along the line connecting A and B and one perpendicular to the line connecting A and B. The component along the line connecting A and B, let's take it in, fine, let's take it in pink color. So you can take one component like this, that is V parallel or VB parallel, I should say. And you can take one component perpendicular to the line joining them. This one, that is VB perpendicular. Tell me, which of these components, VB parallel or VB perpendicular, has the ability to change the distance between A and B? Which of them can change the distance between A and B?
VB parallel, sir.
The component parallel to the line joining them can take B away from A or can take B closer to A. VB perpendicular cannot change the distance between A and B. It can only make B go around A without changing the distance. Okay. Now, for an object to be considered a rigid body, the distance between two particles must not change. For the distance between two particles to not change, okay, I'll copy this diagram. You know which components have the potential to change the distance between them now. Okay. So one of you tell me, or think about it, I'll ask one of you. For the distance between A and B to remain constant, what exactly is the condition? Think about it. Should their velocities completely be equal, or what exactly is the condition is my question. Aishwarya, can you tell me?
So V parallel should be equal to VB parallel.
VA parallel should be equal to VB parallel, correct. Okay, I'll write them as A parallel and B parallel. Okay, A parallel, A perpendicular. So their actual velocities could be in any directions. They could have any magnitude. Okay. The only thing that must be common to both of them for the distance between them to remain same is that the component of A's velocity along the line connecting them should be equal to the component of B's velocity along the line connecting them. If that is ensured, then the distance between them will remain fixed. What are the other components doing? VA perpendicular and VB perpendicular. What do? They make these objects rotate around each other without changing the distance between them. The one that affects the distance is the parallel component. The one that affects the rotation or the orientation is the perpendicular component of velocity. And parallel to what? Perpendicular to what? The line connecting two particles. So this is the condition for a rigid body. Velocities of any two particles along the line connecting those particles must be equal. Okay. Now see, the complete velocity A, VA, as a vector, you can write it as the sum of VA parallel component and VB parallel component. Sorry, why am I saying VB parallel? VA perpendicular component. Okay, a vector can be expressed as the sum of its orthogonal components, means perpendicular components lying in the same plane. That's the idea we are using. So VA vector is the sum of VA parallel vector and VA perpendicular vector. Similarly, VB vector, velocity of B, is the sum of VB parallel vector, sum of its components, that's all, and VB perpendicular vector. Like how we express a vector as the sum of its x component and y component. Here I'm expressing these as the sum of parallel component and perpendicular component, okay, to the line connecting the two particles. Okay. Now think about their relative velocity. Can one of you quickly tell me how to calculate velocity of B relative to A? What is the basic formula for it?
VB minus VS.
Total velocity of B minus total velocity of A. Now, if you subtract VB vector and VA vector, this one and this one, VB parallel, VA parallel are same. Okay, we are considering rigid body. No, we are deriving the condition for a rigid body. VB parallel is same as VA parallel. So when you subtract VB and VA, when you do VB minus VA, those components will get cancelled. What will you be left with? You'll only be left with velocity of B perpendicular to the line joining them minus velocity of A perpendicular to the line joining them. And this basically becomes their relative velocity, not along, it is the relative velocity perpendicular to the line connecting the particles. So in case of a rigid body, these two are equal. Therefore, the relative velocity of any two particles that you take in that rigid body should only be perpendicular to the line joining them. If at all it is there, it should be perpendicular to line joining them. They cannot have relative velocity parallel to the line joining them. Okay, it makes sense from this diagram itself. You can tell VA parallel is same as VB parallel, no? Then if the components, parallel components are equal, then the relative parallel velocity becomes 0. Okay, so along the line connecting them, the relative velocity should be 0. Perpendicular to the line connecting them, they can have relative velocity. Okay, because rotation is allowed. Rigid bodies can rotate without the distance between particles changing. So this is the mathematical condition for a rigid body. This is the relation between any two, relation between velocities of any two particles of a rigid body. Their components parallel to the line joining them should remain constant. Now there are very interesting applications of this also. Consider a rod, rigid rod. Let's say it is like this. And I tell you that velocity of one end of the rod, I'm marking one end in orange. Let's say velocity of this end of the rod is 20 meters per second. Okay, it's moving in some random manner. Let's say you're playing pen fight and you strike the pen at one end. You know it rotates, it moves forward, it undergoes some complicated motion. But definitely rotation will be involved in most cases. And if rotation is there, different particles can move with different velocities. So let's say this end of the rod moves with 20 meters per second at an angle 53 degrees. And the other end of the rod, assume, is moving with a velocity somewhat like this. Okay, we know the direction in which it is moving, but we don't know how fast it is moving. Let's say it's moving at an angle 37 degrees with the rod. Calculate V. The rod is a rigid object. Okay, so the distance between the orange dot and the green dot must not change. And you know the condition which keeps the distance constant. Use that condition and derive V. Type your answers in chat. Saket, can you tell the condition between or the relation between velocities of two particles in a rigid body?
So they need to be equals.
Should the velocities be equal, then V is 20.
No, sir. I mean the component in which the direction of in the direction of distance, the component, the velocity, that velocity should be equal.
Okay. Their velocity components along the line connecting them must be equal. Okay. Just write the condition based on that. Okay. I got 3 answers. Fine. Rishi, tell me, how much is the component of the orange particle's velocity along the line connecting them? Line connecting them is the rod itself. How much is its velocity component in this direction? No response. Okay, Saket, tell me how much is this component?
So 12 meter per second.
20 cos 53, 12 meters per second. Correct. Now, other ones, velocity v is unknown, the magnitude is unknown, but it makes an angle 37 degrees with the rod is what we know. In terms of v, how much is this component? In terms of v, Saket, how much is the component along the
V of 4 by 5, sir.
v cos 37, v 4 by 5, that is 4v by 5. That's all. You just equate these two and your answers are correct only. 60 by 4, 15 meters per second. Okay, you just have to write 12 is equal to 4v by 5 and solve for v from there. Okay, so if you know velocity of one end of a rigid body or one particle of a rigid body, you can tell a few things about the another particle of the rigid body. Okay. Next, this case is quite common actually. There are different ways to solve this problem, but let's use this rigid body idea to solve. Suppose there is a rod, okay, which is resting against the wall, not resting, which is placed against the wall like this, but you leave it. If the wall and floor are both smooth, we know the rod is going to slide off. Okay, it can't be balanced there. You can think of it as a rod or a ladder. We are looking at it from the side. Okay, assume it is sliding off. Wall is smooth, floor is smooth, so the rod is not able to stay in that position. It is sliding off. Can one of you tell me in which direction the upper end of the rod will be moving if the rod is sliding? Exactly in which direction will the upper end be moving?
Downwards.
Downward. It will stay in contact with the wall, no? But it is moving. Staying in contact with the wall, if it has to move, then it has to move like this. Okay. Let's say it's moving down at this particular instant with a speed 5 meters per second. And the lower end of the rod, mark it in blue, it has to slide on the floor, along the floor. Let's say it's sliding with some speed v. If this angle is 60 degrees, calculate v. Do it all of you. What is the speed of the other end of the rod? Type your answers in chat. The rod is a rigid body. You can make use of that fact. I got one answer as 5 root 3. We'll see. Others also send your answers quickly. One more answer also has 5 root 3. Okay. 5 root 3 I think is correct only. See, we have to use the same idea again that the velocity of two particles along the line connecting them, or the velocity component of particles along the line connecting them must be equal. Okay. If this angle is 60, the other angle will be 30 degrees. Saket, tell me, what is the component of, okay, let's name the ends as A and B. What is the component of A's velocity along the line joining them?
5√3, sir.
No.
5√3/2, sir.
5 cos 30 will be 5√3/2. Okay. Now B's velocity is unknown. The magnitude is unknown. But what is its component in terms of V only? What is its component along the line connecting them? Saket.
Sir, V/2, sir.
If that angle is 60, this angle will also be 60. What are such angles called? Opposite angles.
Vertically opposite angle.
Vertically opposite angles. Fine. Then this component will be V cos 60, that is V/2. That's all. You just have to equate them. So 5√3/2 is equal to V/2. V becomes 5√3 meters per second. So if you know the exact direction, then you can tell the magnitude. There is another way also to solve this problem actually. One end's velocity is known. I'll explain the other method. Do any of you know any other way of solving this? Like some of you may have learnt in school. We use differentiation. We use Pythagoras theorem. Okay, let me explain. So we won't talk in terms of components now. We can clearly see there's a right angle triangle forming here. Let's call this distance as y and this horizontal distance as x and the length of the rod as L. As the rod slides, at one instant it's in this position, but at a later instant it may be like this. Okay. So as it slides down, what happens is y decreases, x increases. But length of the rod remains the same. It's a rigid body. L remains same. So x and y are variable, L is a constant. And if you apply Pythagoras theorem, at any instant, x square plus y square should be equal to L square. X and y change, but L remains constant. And x and y change in such a way that x square plus y square is equal to L square, always. Okay. Now what we are looking for is the speed of the end B. Speed of B is nothing but the rate at which this distance x changes. Do you all agree with this or not? Is the speed of B equal to the rate of change of x or not?
Yes, sir.
Okay, it will be. Speed is basically rate of change of distance. Okay, so since V is along the x-axis, V will be equal to dx by dt. So what we need is dx by dt in this problem. And if you need dx by dt, the only thing you can do is differentiate. So you will have to differentiate this equation. But you'll need to differentiate it with respect to time. Okay. So derivative of x square with respect to time plus derivative of y square with respect to time will be equal to derivative of L square with respect to time. Because x square plus y square is equal to L square. Can any of you tell me what is the derivative of x square with respect to time? Okay. What is derivative of x square with respect to x?
2x, sir.
2x. But now you are differentiating with respect to time. So what rule of differentiation should be applied when you are differentiating a function with respect to some other variable?
It's a chain rule.
Chain rule, correct, correct. And let's briefly revise that. We want derivative of x square with respect to time. We know derivative of x square with respect to x. You just multiply that with dx by dt. It becomes derivative with respect to time. Simple. So this first term can be written as 2x dx by dt. Plus the second term will become 2y dy by dt equal to, now L is a constant, L square will also be a constant. Derivative of a constant with respect to any variable is 0 itself. Okay. What we are looking for is this. So let's keep that on one side and write the other terms the other side. You can say that dx by dt is equal to, the 2's get cancelled. Send it that side, minus y divided by x dy by dt. Okay. Now, in this right angle triangle, for 60 degrees, y is the opposite side, x is the adjacent side. Y by x becomes tan 60. Tan 60 is root 3. And dy by dt, rate of change of y is nothing but this speed, 5. But as the rod comes down, y is actually a decreasing value. Y changes at a rate 5 meters per second, but it is negative change because it is decreasing. So dy by dt is actually minus 5. Minus minus cancel. You get dx by dt as 5 root 3. That's the speed we are looking for. But this is all mathematical. Okay. The other method, I prefer the other method. If it's a rigid body, just use the fact that their relative velocity along the line joining them should be 0. Or you can say their velocity components along the line joining them should be equal. Based on that, you can easily calculate the unknown velocity. Fine. So this is one thing we can say about rigid bodies, that the relative velocity of any two particles along the line joining them should be equal. Sorry, relative velocity should be 0. Velocity component should be equal along the line joining them. Another thing we can tell about a rigid body, okay, you consider this system itself. Just a moment, I'll have to show two different orientations of this. Assume this is one orientation. 1 second. Okay. See, it's the same system, but rotated. Fine. Okay, it's looking bigger. Okay, consider it like this. It's a rigid body which has been rotated. Fine, I can in fact make them overlap also. It's a rigid body which has been rotated. So the particles have changed their position. Most of the particles have. It's possible that all particles have changed their position also. And you can see that the line connecting A and B has rotated by some angle. Now, not just A and B, take another pair of particles. Let's say this one, C and this one D. The line connecting C and D is like this. Okay, in the other image, if you see, this is C, this is D, this is the line connecting them. Okay. You can take two more particles also if you want, say E and F. Let's take them separately. Maybe this is E and join it to F. So in this image, if you see, this is E joined to F. Okay. Now all these lines have changed their orientation. They have all rotated. From your intuition, or you can literally put a protractor and measure if you want. But tell me, do you think all the lines rotated by the same angle or not? Do you think all the lines rotated by the same angle or not? I can make it overlap if you want so that you can check the amount of rotation. But okay, it's a little clumsy. Aishwarya, what do you say? Do you think all of them rotated by the same angle or not?
So yes.
Saket, what do you think? Okay. See, they would all have rotated by the same angle. You can check it if you want. What I suggest you do is take a cardboard, okay, or you take any solid object that you can find, draw some lines on it, rotate the object, and see how much each line has rotated. You will see that every line that you draw rotates by the same amount, okay, compared to its previous orientation. And all this would have happened in the same amount of time. Let's say they all rotated by an angle delta theta in a time delta t. Then their angular velocity would have been delta theta by delta t, which is common for every pair of particles. Okay. So in a rigid body, all particles rotate with the same angular velocity. They cannot rotate at different rates. If they rotate at different rates, no, then the object will get twisted. It's like when you try to wring clothes. Okay, when you want to drain off water from a cloth, what you do? You hold one end of the cloth, like you first make what? How do you say? You first make it into a lump, and then you hold one end, you twist the other end. Okay, when you hold one end, that end is not moving. Those particles are not moving. When you twist the other end, they are rotating. So different rates of rotation. Or you could do the opposite also. One rotates this way, the other end rotates the other way. Okay, so they rotate at different rates. Then the object gets twisted. If they rotate at the same rate, object will not get twisted. And we are talking about rigid bodies. Rigid bodies cannot be twisted. Therefore, all particles of a rigid body must rotate with the same angular velocity. Or you draw a line connecting any pair of particles in a rigid body, all the lines must have the same rate of rotation. Otherwise, it's not a rigid body at all. Okay, so this is another condition for a rigid body. Omega of the particle A should be equal to omega. Omega means angular velocity. Should be of the part equal to particle C, or let's name them one to number them. Omega of the first particle should be equal to second, should be equal to third, should be equal to omega of the nth particle. So in a rigid body, different particles having different angular velocities is not possible. Linear velocities can be different, okay, because V is equal to R omega. So depending on the distance from the axis of rotation or the center of rotation, they can have different speeds, but the rate of rotation should be the same. Otherwise, the object will get twisted and it can't be considered a rigid body. Okay, so we'll stop it here for now. So what we discussed in today's class is how what we are going to study in this chapter is different from what we studied before. We are now including rotation in a system and how to account for it. Okay, and I gave you some examples. If you want to write the total momentum of a system where different particles move with different velocities, it will be impossible to add the add the momentum of each particle separately like this. So we need some other ideas to do it. Those ideas are what we are going to discuss in this chapter. Similarly, kinetic energy and some other quantities also. Okay. Then we talked about what a rigid body is. What is the mathematical condition for a rigid body? Velocity condition is that the components of velocities of any two particles along the line connecting them should be equal. Okay. We solved 2 questions based on that also. And then we discussed the condition between angular velocities. Angular velocities of all particles should be the same. Okay. Otherwise, the object will get twisted, and twisting is not allowed in a rigid body. Okay. Next class, we will discuss a very important concept actually. There is, for any system, we can identify a special point which will help calculate these things very easily. Be it linear momentum, kinetic energy, potential energy. Okay. It makes it easy for us to calculate these values for a system. Not just these values. If you can identify that point and see and visualize what that point is doing, then describing the motion of a rigid body which undergoes rotation becomes very easy for us. Okay, it's called center of mass. So next class we'll talk about center of mass, how to identify, okay, and what are the different kinds of motion that a rigid body can undergo. Those things also we'll discuss. Okay, thank you all. We'll continue on Wednesday. Or see, I may take a 1 hour class tomorrow. I'll inform the timings. Otherwise, it will be on Wednesday.
Thank you, sir.
Thank you.